In this video, we'll analyze the energy stored in a capacitor. We know there's energy stored in the electric field between the plates of the capacitor. When we first connect a battery or some other device to do the work to put charge on the plates of the capacitor, an electric field is going to have to set up to distribute the charge. So initially, when our switch is open, there is no electric field between the plates of the capacitor. There's no charge on the plates of the capacitor, and there's no potential difference across the plates of the capacitor. Once we close the switch, an electric field sets up in those wires between the terminals of the battery and the plates of the capacitor. And we have these potential surfaces that will eventually become equipotential surfaces, but not until after the charge redistributes. Electrons are going to move in the opposite direction of this electric field. So electrons will move from the positive plate of the capacitor to the positive terminal of the battery, and from the negative terminal of the battery to the negative plate of the capacitor. Electrons are moved in this process as charge builds up on the plates of the capacitor, and electric field builds up between the plates of the capacitor. As more charge moves to the plates of the capacitor, the electric field between the plates of the capacitor gets stronger. And in that process, more work is required by the battery to transfer that charge. This electric field being set up between the plates is opposing the direction of a negative charge moving from the positive plate to the negative plate. Negative charge between the plates of the capacitor is going to want to move in the opposite direction. So the effect is that this electric field building up is opposing the electric field being set up by the battery to do the work to charge the capacitor. So more work has to be done by the battery to move each successive incremental charge. The easiest work is done initially, and at the end the work gets much more difficult, to speak. So the work done by that external agent, in this case the battery, at the expense of chemical energy, is stored then as electric potential energy between the plates of the capacitor. So again, if we consider that the charge is transferred in a closed loop, then what we're considering is that charge is being transferred from negative electrons are being transferred from the positive plate of the capacitor to the negative plate of the capacitor. Clearly, work is going to be required by an external agent, since this electric field is going to want to push electrons in the opposite direction of the electric field, not towards the negative plate of the capacitor. So we know the external agent must be doing the work. If we assume that at any given instant we have some Q prime, or some differential amount of Q, small amount of Q, that has been transferred from one plate to the other, then the potential difference then at that moment that will exist across the plates of the capacitor will be some plus or minus V prime, which of course will, that's V prime, which will be equal to our Q prime over C, according to our theory. If an incremental charge is then transferred, the work to be done to move that is going to be our VQ, so it's our V dQ, or our Q over C dQ. So the total work then that's being done is the integral of all the work, so that's 1 over our capacitance. We can pull that out of the integral, integrating over the total charge of our Q prime dQ prime, so we end up with a Q squared over 2, and we still have the 1 over C. So we have Q squared over 2C, and what's that? That's the work being done by an applied agent, so our work applied is equal to the electric potential energy. So the electrical potential energy stored between the plates of the capacitor, we can state it in terms of the charge on the plates of the capacitor. It's 1/2 that charge squared divided by the capacitance, or we can use our theory that the charge on the capacitor is equal to the capacitance times the voltage across the plates of the capacitor, and we can substitute that and we get potential energy is also 1/2 CV squared, and we can get potential energy in terms of the potential difference across the plates of the capacitor. So in summary, we have two theories for calculating potential energy stored in the electric field. We can use, if we know the capacitance and the charge on the plates, if we know the capacitance and the potential across the plates. But then again, if we substitute in for C, C is equal to, or well, let's substitute in for C. C is equal to what? C is equal to Q over V. So we get our potential energy in terms of charge and voltage is 1/2 QV. We know we have the theory that the change in potential energy of a point charge is equal to Q times the change in voltage where that point charge is going to exist. So that's different. That's for a point charge. This is a potential energy for a capacitor. If you recall what we said, as we're incrementally adding charge to that plate, the work required to do that increases, so we end up with this 1/2 QV for the potential energy for a capacitor. So potential energy stored, it's independent of the geometry of the capacitor. It's just dependent upon the capacitance itself. The energy then, once we've stored it, is a potential energy, so we can recover it in terms of kinetic energy, and that's when that charge moves, and that becomes current. We'll learn more about moving electricity, current, and that's our example of a photoflash or a medical defibrillator that can, the rate at which that energy can be delivered is quite high, so it has a good power for a small amount of energy that's stored. We'll also talk about capacitors in parallel and capacitors in series, and we'll see that two capacitors in parallel will store a larger amount of energy than two in series. So let's look at an example of two physical capacitors. They're geometrically equivalent, but capacitor 1 has twice the plate separation as capacitor 2. So we're going to consider an example where they have the same charge, Q, on their plates. And what we want to compare is their electric potential energy stored in the field between their plates. So we'll assume for a moment that they're parallel plate capacitors. What we're given is they're geometrically equivalent. So the area of the plates, the surface area of the plates, we'll set that to be the same. A1 is equal to A2 is equal to A. But we know that the plate separation in C1 is twice that in C2. So we'll draw our diagram, and our D1 will have a distance of 2D, and our D2 will have just a distance of D. So we'll let our D1 equal D, and our D2 equal, our D1 is equal to 2D, and our D1 is equal to D. So we can first look at the capacitance itself. We want to know, we want to compare what? We want to compare the potential energy, but let's first look at the capacitance. If we compare the capacitance of the two, since our capacitance is proportional, C is equal to epsilon naught A over D, is inversely proportional to the distance between the plates, then the greater the distance between the plates, the smaller the capacitance. So we can show that our capacitor 1 has half the capacitance of capacitor 2, since they have the same area of the plates. So now what we want to find, if they have the same charge on their plates, we want to compare the electric potential energy stored in the field between their plates. So showing the same charge on the plates, we know capacitor 1 has half the capacitance, and now we have two theories for electric potential energy. We have 1/2 CV squared, and we have 1/2 Q squared over C. But what's the same between these two? What we're given is the same as the charge. Let's use this theory for potential energy, and we'll see that our potential energy in capacitor 2 and potential energy in capacitor 1, the only difference is the capacitance. So the potential energy in capacitor 2 divided by that in capacitor 1 has an inverse relationship. So since C1 is 1/2 C2, potential energy of capacitor 2 is 1/2 that of capacitor 1. So there's more potential energy stored in the capacitor with the least capacitance. It has the most volume there to store energy. Let's do some check there. Let's check the voltages. We know our relationship between voltage and capacitance if for the same charge on the plates, the voltage across capacitor 2 here, V2, V1, V2 is Q over C2, V1, Q over C1. Since C1 is 1/2 of C2, then we have that V1 then is going to be twice V2. So we have twice the voltage across the capacitor with the smaller distance between the plates. Twice that voltage, same charge on the plates. So in this volume, we're going to end up storing more energy in that electric field. So the other thing we want to look at, we looked at potential energy storage in the electric field between the plates of the capacitor. Well, we can also look at the energy density. Energy density is an important concept. How much energy can you store within a volume? If you can store more energy in less volume, then that's nice for our little small gadgets that we like to carry around, or if we want to put that energy in a car, we'll have less mass, potentially taking up less space. So let's consider a parallel plate capacitor, and again we'll neglect the fringing and the so the electric field will be the same at all points between the plates. So we'll look at potential energy per unit volume. That should also be uniform. So we use a lowercase u for energy density. That's our potential energy per volume for a parallel plate capacitor. That volume is the area of the plates, right? The area of our plates up here. And then we'll multiply that by, here's our area, there's our distance between the plates. So that volume in there, AD, for potential energy, we'll use our 1/2 CV squared. And then we can substitute in for our capacitance is epsilon naught A over D, and then we can do a little bit of algebra here, and we end up with a D squared. We have 1/2 epsilon naught V over D squared, but that V over D, that's our electric field, right? So that's our for a uniform field, our voltage is equal to ED, or electric field is voltage divided by distance. So we have 1/2 epsilon naught E squared. That's going to be true for all types of capacitance, no matter the shape, true for whatever the source of the electric field might be. So if we look at consider an example of a charged isolated metal sphere, we know its diameter, we know the electric potential at the surface of the sphere relative to a zero at infinity. We want to calculate the electric density, energy density of the electric field in the area of space near the surface of the sphere. We know that the radius, we'll consider that the radius, capital R I guess, is equal to the diameter divided by 2. And we know the electric potential at R is equal to capital R is 8,000 volts. We want to find the energy density. We need our theory for electric potential. We can use that theory for a point charge, right? We can use our shell theorem. It will be the same, KQ over R. Our electric field now in the radial dimension, our R dimension, dV dr. And we have our theory for energy density that we just looked at, 1/2 epsilon naught E squared. If we substitute then in, start looking at our electric field, the magnitude then, KQ over R times 1 over R, well that's our V over R. So it's looks like the uniform electric field a little bit, huh? So then we can plug in for our electric field at R is equal to 0.05 meters. That's our 8,000. So that's our voltage, 8,000 volts, and then our 1 over R, 1 over 0.5. So we know our electric field then around the surface of the sphere, so we can determine our energy density being 0.11 joules per meter cubed.